Special relativity assumes two things: that the physical laws apply in all inertial frames of reference, and that the speed of light is constant and independent of relative motion. Assuming these two postulates, you can also reference a light clock. A light clock works by having a particle beam shoot up, or particle beam of light, shoot up, reflect off a mirror, and back down. To complete one oscillation is 1 second. Now, there are two different types of time. One is relativistic time and one is absolute time. If this light clock is traveling at the same velocity that I am, it would be considered my relativistic time would also be photons of light, absolute time. If I were to accelerate this light clock to a velocity greater than my own, I would find that the distance, or the path that the light will travel, is greater than if it were to be straight up and down. This could be illustrated by taking an ordinary object, throwing up in the air, and back down. If I give it only a vertical velocity, the distance that it travels will be less than if I were to give it a horizontal velocity and a vertical velocity. This also works for light too. If the light clock is moving, the path that light takes will be greater. And this could be referenced through the Pythagorean theorem. But first, we need to define these three vectors. This vector can be defined as the product of the speed of light and relativistic time. This vector, vector L, this is vector S, but vector L can be defined as a product of velocity and relativistic time. And this vector, vector D, can be referenced through this same path, which is the product of the speed of light and absolute time. Now, we can also derive an equation for time dilation, which is solving for relativistic time. If I were to use Pythagorean theorem, connect all of my variables, I will find that time dilation is equal to, or relativistic time is equal to, delta tau, which is absolute time, over the square root of 1 minus v squared over c squared. By analyzing this equation, I can say that the greater that this light clock is traveling, the greater the value for relativistic time, or the greater the amount of time dilation there will be. To illustrate this point, I can reference a particle accelerator experiment, and I can say that a pion, since its time that it decays is 2.6 times 10 to the negative 8 seconds, its velocity is close to the speed of light, and its displacement is a product of its velocity and its time, which would be, if you were to solve for displacement, you would find that displacement is equal to close to 8 meters. This is ignoring special relativity and time dilation, but if you were to accept this principle, you would find that the time that the particle is actually traveling for is 100 times greater than it takes to decay. If you were to ignore the classical interpretation of displacement and accept the new version of displacement, you would say that the displacement is equal to the pion's velocity and its relativistic time, which is close to 800 meters, 100 times greater than the original displacement. By accepting the theories of special relativity, particle accelerator experiments can become more and more accurate, predictions become more and more accurate. And the reason why I chose this topic was because I plan on becoming a particle physicist and throughout my college career studying particle physics. In order to become a greater scientist and a greater teacher, a greater learner, I need to teach myself fundamental principles of the universe, basically, that relate to particle physics and physics alike. The reason why I do this is so that way I can not only become a better person, more intelligent person, but also increase my chances of benefiting humanity for the better.